So far, we've talked about motion in one dimension. Remember, motion in one dimension is motion along a straight line. It can be forward or back, up and down. Now we're going to talk about motion in two dimensions. Motion in two dimensions, we're talking about maybe motion is forward and back and up and down. A projectile is a good example of an object that moves in two dimensions. A projectile is anything that is acted on only by gravity. If you throw or kick or shoot something into the air, as soon as you stop applying force to it, it is considered to be a projectile. So a projectile's acceleration is downward. It accelerates downward at 9.8 meters per second squared. This is what we refer to as g, or the acceleration due to gravity. This is a constant. G equals 9.8 meters per second squared. That's true on Earth. If you were not on Earth, then the value of g would change, and that's due to the gravitational force of Earth. And it is 9.8 meters per second squared, whether you're talking about a large object or a small object. Now we're going to look at some projectiles, particularly these two in this image, and we're going to analyze this and ask, are the horizontal and vertical motions of the two projectiles the same? Well, let's enlarge this. If we look at the red ball is accelerating downward. It's definitely accelerating downward because we can see that the intervals between the balls, or it's one ball, but the intervals between the images of the ball are increasing in size with each successive image. And these images are taken at equal time intervals. So that means that over time, the distance that the ball travels in the same amount of time is increasing. Now notice everywhere vertically where there is a red ball, there is also a yellow ball. Okay, so what we're seeing here is an image of a red ball that was dropped at the same time, the exact same time as that a yellow ball was launched horizontally. So the yellow ball is shot to the right, the red ball is dropped straight down, and we notice that they fall downward. They both accelerate downward at 9.8 meters per second squared. The difference is that the yellow ball is also moving to the right, but they fall at the exact same rate. That's an important point to pay attention to. When we talk about projectiles, like a basketball, for example, is a projectile. As soon as you release the basketball, or as soon as this young lady releases the basketball, it's going to follow a predictable path. It's going to follow what we have referred to as a parabolic path. The motion of this basketball, this projectile, can be broken down into horizontal and vertical components. Often it's useful to look at horizontal motion and vertical motion separately from each other. We can see that the ball is definitely following a path like this. It's following a curve, and when she releases the ball, she can predict what path that ball will follow. That's why she's able to score a basket. However, even though the ball is never moving perfectly horizontally or perfectly vertically, we tend to look at the horizontal and vertical motion of that ball. If we look at the horizontal motion, let me get my face out of the way. If we look at the horizontal motion, we can see that the ball is moving horizontally at a constant velocity, constant rate. Each of these balls, or each of these images, is an equal distance from the previous image, right? So the ball is moving left to right at a constant rate. Why? Because it has no force pushing it. As soon as she lets go of the ball, it will move forward at a constant rate. However, what's it doing vertically? Well, vertically it moves up, and it slows down as it moves up until it reaches the top of its path, and then it starts speeding up as it moves back down. Why? Because now it has a force pushing it down. It has the force of gravity, and gravity will cause it to accelerate downward at 9.8 meters per second squared. We use arrows to describe vectors. Okay, vectors, we already learned the term vector. A vector is a measurement that has both magnitude and direction. Here we see vectors used to represent displacement. So we have a displacement of 10 meters to the right, then 10 more meters to the right, then 20 meters to the right. Remember, displacement is a vector. It has both magnitude and direction. When we draw an arrow, we often just say we're drawing a vector, but what we're really doing is we're drawing an arrow to represent a vector, because the vector is the actual measurement or the actual quantity that has both magnitude and direction. So vector variables in your textbook are given in bold print. A scalar, remember, is the other kind of measurement. It's a measurement that has magnitude but not direction. So a scalar might be something like mass or temperature. The scalar, we had a question in class that said, okay, if the velocity of something, and these are the wrong numbers, if the velocity of something is -6 meters per second, it was a runner. The velocity of a runner is -6 meters per second. What is his speed? Well, if the velocity is -6 meters per second, -6 meters per second, that means that his speed is 6 meters per second. So that's his speed. And his direction is in the negative direction. Speed is a scalar, velocity is a vector. We do this a lot in physics. We draw arrows to represent vectors, to represent vector quantities, and we do it in a very precise way. We pay attention to the relative length of our vectors. The longer the vector is, the greater the magnitude of the vector quantity. So if you're going to show something has twice the velocity of another object, if object B has twice the velocity of object A, then the arrow that you draw to represent the velocity of object B should be twice as long, and it should be pointed in the correct direction. Here we see vector A added to vector B. If we want to add two vectors that are in the same direction, we can actually take this vector, vector B, and we can move it. As long as we keep it pointing to the right, pointing in the same direction, we can move this vector B to where it is lined up with vector A, to where the head of vector A is in contact with the tail of vector B, and then we can say A plus B equals C. C is the sum, or what we call the resultant, of those two vectors. When we add two or more vectors together, we get what's called the resultant. The resultant, that's like saying the sum when we're talking about vectors. Here we have a subtraction problem with vectors. If we want to say vector A minus vector B, then we take vector B and we turn it around. We reverse its direction. And then so vector B pointing in the opposite direction is vector negative B. So A minus B, remember A minus B is the same as saying A plus negative B. So this little vector right here, that's negative b. So if we take the tail of vector negative b and put it in contact with the head of vector a, then we see that then we can take the length of vector b away from the length of vector a, that we can take that magnitude away, and we can see that the length of vector a is, or the length of vector c, I'm sorry, is shorter than vector a was. We're going to do some practice with this, so we'll definitely get a lot of practice with this. There are two ways to add vectors together. One is what I just showed you. We can put the head of one vector touching the tail of the other vector. Here we see, and it doesn't matter in which order you go in. Just remember, like in math, it doesn't matter if you do a plus b or b plus a. If we move one vector, as long as we keep them pointed in the same direction, we move one vector so its tail is on the head of the other vector. And then we get the resultant vector c. This is vector c, right? They form a triangle. When you add two vectors together, the third vector is the one that goes from the tail of the first vector to the head of the second vector, vector c. Another way to add vectors together is by using the component method. When we have a vector that is not vertical and not horizontal, it's pointing at some kind of a diagonal, we can say that, okay, vector A is equal to a sub y plus a sub x, right? This is vector A. Vector A is pointing at a diagonal, and it can be vector A can be the resultant of a vertical vector a sub y and a horizontal vector a sub x. Same thing with vector b here. So we have vector b at an angle. We can say that vector b is the resultant of b sub x and b sub y. Well, if we want to find what vector c is, instead of dragging vector A over and putting it head to tail with vector B, now we have two vectors that are parallel to the y-axis and two vectors that are parallel to the x-axis. So it's very easy to add them together. We can add a sub x plus b sub x. We can add a sub y plus b sub y. And then that resultant is C, and you would get the same result, right? You would get the same answer whether you use the head to tail method or whether you use the component method. The component method is sometimes very helpful, especially when we get to more complex vector addition problems and vector subtraction problems. We use, you should have learned how to do trigonometry in geometry, I believe, in some math class. But trigonometry takes advantage of two big concepts. One is the Pythagorean theorem, right? The Pythagorean theorem says that in a right triangle, a squared plus b squared equals c squared. If this is a and this is b and this is c. Okay, you've learned that before. But then there's another concept which uses trigonometric functions, sine, cosine, and tangent. And as a review, you may have learned SOHCAHTOA. Okay, SOHCAHTOA tells us the definition of sine, cosine, and tangent. Sine, the sine of a side, the sine of an angle, the sine of theta is equal to the opposite side over the hypotenuse. That's so. The cosine of theta is equal to the adjacent side over the hypotenuse, and the tangent of an angle is equal to the opposite over the adjacent. Okay, we'll review this in class in case you have difficulty with it, but we'll get some practice with this as well. So trigonometry tells us the relationships between the sides and the angles of triangles, specifically right triangles, because horizontal and component vectors are based on right triangles. We can establish trigonometric relationships and use them to find the lengths of different vectors and the angles between them. So when we put vectors together to make triangles, then we can learn a lot about the angles of those vectors, about the magnitude of those vectors. Velocity has magnitude and direction. A change in velocity can be a change in speed, as when a falling object accelerates, or a change in direction as when a ball recoils or bounces off the ground, or both. So velocity is a vector quantity. So the velocity of an object changes when it either speeds up, slows down, or changes direction. This is called acceleration. We learned that in the last lesson. If a ball, we saw also in the last lesson we saw an example of a ball rolling, hitting a spring, and then bouncing back. So in order for it to bounce back, it had to slow down, it had to stop for a moment in time, and then it had to accelerate back in the other direction. If we were talking about, so the reason that it had to slow down and stop and then come back in the other direction is because we were focusing on one-dimensional motion. In two-dimensional motion, an object can change direction without slowing down. Here we see two-dimensional motion. We see motion in the horizontal, and we see motion in the vertical. If we fire this cannonball off of this cliff, it's going to follow the parabolic path that you see here. And I'll draw it very badly. But if we break down the motion of that cannonball into its components, we can see what we saw in the earlier slide where we had the yellow and red ball, right? We had the yellow and red ball, and one was dropped straight down and the other was launched horizontally. Well, if we look at the cannonball and we break the motion of the ball at different points in time down into its horizontal and vertical components, we end up with a diagram that looks very similar to what we saw with the red ball and the yellow ball. We see the equivalent of a ball being dropped straight down, and we see the equivalent of a ball being launched horizontally at a constant speed. So this shows constant speed in the horizontal dimension, and it shows acceleration in the vertical dimension, and that's how we end up with this parabolic shape. If the acceleration of the object is parallel to the direction of the object's motion, then the object will slow down or speed up. So if the acceleration and the motion are in the same dimension, acceleration and velocity are in the same dimension, either the same direction or opposite direction, then the object will slow down or speed up. If the acceleration is perpendicular, like here, we see the acceleration is down and motion is horizontal. If the acceleration is perpendicular to the direction of the object's motion, remember, right when this cannonball is launched, its motion is perfectly horizontal until it starts, until it leaves the end of the cannon, and then it starts accelerating downward, starts falling. So we have acceleration being perpendicular to the direction of the motion, and that causes the object to turn in the direction of the acceleration. Here we have a projectile, so that means that it's turning downward. But this is true even when we're talking about non-projectiles. So let's look at this. For each graph, is the acceleration constant or changing over time? Remember, when you look at a graph, it's very important to look at the axes, what's being graphed. Here we have velocity versus time. So if we look at the velocity versus time, we can see that in the first graph, this is the wrong unit. So time should be measured in seconds. Sorry, I just noticed that. Time is in seconds, not in meters per second. So we look at, is the acceleration constant or changing over time? Well, in each of these, we see the velocity is constant, right? In each one, we see constant velocity because we see a straight line. And the slope of a velocity versus time graph, the slope of a velocity versus time graph, the slope, not stope. Let's see if I can spell now. The slope of a velocity versus time graph is going to be the change in velocity over the change in time. This is the definition of acceleration. Change in velocity over change in time. So we see that the steeper this gets, the steeper this ramp gets, the steeper the slope of the graph gets, which means that the greater the acceleration. Okay, but we see in all four examples, we see positive acceleration.